Hi, greeting fellow calculus fans. Today we're going to learn a new method of integration called integration by parts. And technically what this actually is just essentially a backwards product rule. So we might want to remind ourselves that by the fundamental theorem of calculus, integration is actually really just anti-differentiation. So, for example, for derivatives, when we're doing the power rule, it says that if you're trying to take the derivative of u to the n, where u is some formula of x's, then we just fall off a cliff, lose a life, and then by the chain rule multiply by the derivative side. So there we go. So fall off the cliff, lose a life, derivative inside. But because of FTC, we can turn this from a derivative rule into an integral rule by essentially just doing this backwards. So for integrals, what we have for the power rule is if we're trying to integrate a formula to a power, rather than multiplying by the old exponent and then reducing it by 1, and then tacking on the derivative, what we have to do is start with the derivative on the outside, and then actually add 1 to the exponent, and then divide by that new exponent, and then of course add on the constant of integration. Alright, well let's see how this would apply if instead of doing it to the power rule, we actually did it for the product rule. So just a reminder, how did the product rule for derivatives work? Well, it says if you're ever trying to take the derivative of a formula of two different x's multiplied together, two different formula of x's, then what you do is you take the second formula multiplied by the derivative of the first, and then add the first formula multiplied by the derivative of the second. Well, again, by the fundamental theorem of calculus, if this is the derivative of uv, then that must mean that when you take the antiderivative of it, in other words, the integral of this entire side, that must actually just be, the formula for the area would just be uv. Now, let's just do a little bit of algebra here. So, actually, calculus properties. So the integral of, remember, this is all just a formula of x's. So if you have a single integral with a sum, we can divide that up into two separate integrals. And let's go ahead and move this integral over to the other side, like so. So this formula right here, I'm going to box this in because this is actually pretty important. This is the formula that we refer to as integration by parts. So it says if you're trying to integrate a formula of two different formula of x's multiplied together, then it comes out to be this crazy thing. Now notice this answer we get still has an integral in it. Okay, so what it really says is just it's a technique of integration. It says if you got some sort of tricky integral, you can convert it into this other problem, which involves another integral, which is hopefully less tricky. So I think this will make more sense if you see an example. So for example, let's do the integral of x sine x dx. So notice we've got two different formulas multiplied together. So if we wanted to get to match up with our formula for integration by parts, then one of these needs to be a u and one needs to be a dv. And we'll explore in a little bit what would happen if you sort of make a mistake and choose the wrong one. But we're going to have the u be the first formula here, which means that the dv is going to be the second formula. And we're going to need to figure out the corresponding derivatives and antiderivatives of these things. So if u equals x, then that means that du would just be dx. I took the derivative of both sides there. And this one you need to think a little bit. If dv is sine x dx, well, what's the v that it came from? Well, v would have to be negative cosine x, because the derivative of negative cosine x would be sine x. So at this stage, all we have to do is apply our integration by parts formula. So this is now of the form u dv. So if this is the integral we're trying to calculate, we rewrite it using this. So it would be u, which is x, times v, which is negative cosine x, minus the integral of v, which is negative cosine x, du, which is just dx. Now, let's just do a little bit of algebraic simplification here. This negative we can pull outside. This negative also goes outside, becoming a plus, like so. So we ended up converting this integral, which was kind of hard because it was two different formulas here, into a separate problem, which is an integral with just a single formula, just the integral of cosine x. And we know what the integral of cosine x is. It's just sine x. So this is just sine x, and then don't forget we still have this minus cosine x there from in front. I sort of changed the order there. And last but not least, we should add on our constant of integration. Now, let's actually do a little double check to see if this is actually the right answer. So, one way we could do to see if this mysterious formula actually worked is, again, by FTC, if this really is the integral of this function, it should be that if I take the derivative of this, it gets us back to x sine x, our original function. So, let's actually just do that. Let's take the derivative of what we think the answer is. So, technically there's a plus c here, but when we take the derivative that would go away, so I'm not going to bother to write the plus c there. So we need to take the derivative of sine x minus x cosine x. Well, what's that going to be? Well, the derivative of sine x is just cosine x, and if we need to take the derivative of x cosine x, we need to use the product rule. So it's not a surprise that when we went in this direction, we had to end up using the product rule, because remember, when we get the forwards direction, we were using the backwards product rule. So it makes sense that when we're undoing it, we'd use the product rule. Well, let's just double check how the product rule would work here. So we get the second thing, cosine x, times the derivative of the first thing, derivative of x is 1, minus the first thing, which is x, times the derivative of the second thing, which is negative cosine x. And I said minus, but I meant plus. Sorry. I was confusing it with the integration by parts. So, all right. So, again, just to reiterate, so the product rule for derivatives, it's a plus right there. So, okay. Well, if we just mentally distribute this minus, so a minus cosine x, that's going to cancel with this cosine x. This minus distributes over here, canceling that minus. So in the end, we just get x sine x. So indeed, when we took the derivative of what we thought the answer was, we did get back to what we started with. So our integration by parts formula served us well. Now, one thing I'd like us to consider, and students always ask this, is what if we had chosen unwisely? So what if we're trying to do the integral of x sine x? What if that if we changed the order around, and maybe just by accident, we had decided to let the trig part be the u, and the polynomial part be the dv? So it turns out mathematically nothing goes wrong if you do this. It just doesn't help you calculate what this integral is. In fact, it just makes matters worse. Because let's see what would happen if we try to do this. So we'd have u would be sine x, so du would be cosine x, and then our dv would be x dx. So that means the v that it came from would have had to been 1/2 x squared. So if we apply the integration by parts formula, what we'd have is u times v, which is 1/2 x squared sine x, minus v du, so I'm going to go ahead and pull out that 1/2 there, so x squared cosine x dx. Well, so instead of having to solve this problem right here, which was a trig formula with an x attached to it, we've converted into this integral, which is a trig formula with an x squared after it. So the problem is just getting worse. It's getting harder. And if we did it again, we'd end up with an x cubed in front, and then an x to the fourth. So we keep running away from what we're actually trying to do. So as a general rule, this doesn't work 100% of the time, but as a general rule, as you sort of see these problems, you'll realize that generally, if you've got two different formulas multiplied together, and one of them is a polynomial, then you should have that be the u, not the dv. Because if you have the polynomial be the u, when you figure out the du part of it, the power is going to go down. And thus hopefully be a simpler type of integral you have to do the next iteration. Okay, so now let's get a tad more sophisticated. So there are sort of three sneaky applications that you might not expect coming out of the integration by parts technique. So, and these are the names that I have for them. They're nesting, and invisible integration by parts, and there's also deja vu. And I'll actually do an example of each one of these. So let's actually start with nesting. So what do I mean by a nesting integration by parts formula? Well, this is a type of problem where after you do integration by parts, you have to do integration by parts again. So there's an integration by parts inside of the integration by parts. And here's kind of the typical example. Suppose we need to integrate x squared cosine x dx. Well, following the rule of thumb that I gave before, this part should probably be the u, and the trig part should be the dv. And off to the side, let's go ahead and just calculate what our individual parts are going to be. So if u is equal to x squared, du is 2x dx. And if the dv is cosine x dx, that means the v had to be sine x, because the derivative of sine is cosine. So now we just go ahead and apply our integration by parts formula, because now it looks like the integral of u dv, exactly set up like it is. So that's going to be equal to u times v, so u times v is x squared sine x, minus, and again I'm just looking at my integration by parts formula, the integral of v, which is sine x, du, and the du is 2x dx. Well, let's do a little bit of math here. I'm going to just pull out the 2 and change the order of that. So it's just 2 times the integral of x sine x. So we converted from this integral to this integral. And this is an easier integral because instead of having a quadratic in front, it's just a linear function in front of the sine. So we could actually do integration by parts on this again. And usually that's what you'd have to do, except this formula might look a little familiar. We've actually already did it. That was the problem we just did. We just did the integral of x sine x. So we know what the answer to that is. So this final thing is actually going to be x squared sine x minus 2 times the answer we got from the last integral. And then don't forget, add on the plus c. Okay, I mean, we got a little lucky there that the nested integral that we had to do was the one we just did. Of course, normally that doesn't happen, and sometimes it nests a few times, so you have to do an integration by parts inside of integration by parts inside of integration by parts, hopefully getting easier and easier each time. All right, well, let's look at the second type of sneaky application of integration by parts. That's what I call the invisible part. So let's take a look at this problem. Let's do the integral of the natural log of x. Now you might be tempted to think, oh, that's just 1 over x, or dx over x. Well, I'm sorry, not dx over x, 1 over x, but that's actually derivative, right? So this is the integral of natural log x. You haven't seen this before. And it turns out this is an integration by parts problem. Now you might say, how is it integration by parts? There's only one function there. Well, this is like an invisible part. You can think of this as being 1 dx. So let's go ahead and split this up as that's our u, and that's our dv. So let me write it out. You got u equal log x. So du is 1 over x dx. And our dv we said is dx. So that means that our v is just x. So now we just apply our handy-dandy formula. So the integral of u dv, which is what we have, is equal to u times v. So u times v, sorry, my v kind of a little messed up there, but so log x times x, I have that there, minus the integral of v du. So the v is x, the du is 1 over x dx. Well, that sort of simplifies nicely. The x and the 1 over x cancel out, so you just get dx. Now, technically I should point out 1 over x and x don't cancel if x happens to be 0, but we sort of know for the purpose of this problem x is never going to be 0, otherwise this integral would have made no sense, right? Because you can't integrate over an asymptote like that. So we know the x is never 0 implicit in this question being asked. So that cancellation was fine. So, alright, well now we've converted this integral problem into this other integral problem. Well, the integral of dx is actually pretty easy. So we just have x log x minus x, and then don't forget to add on the plus c. Alright, and last but not least, the third sort of sneaky application of the integration by parts formula is what I call the déjà vu category of problems. So this is when you do an integration by parts problem, and it turns out after doing it, you sort of end up back with what you started with. You're like, I've seen this question before, it's what I started with, but it turns out that's not always a bad thing. So let's look at the typical example. So let's try to do the integral of e to the x sine x. So it's not clear which we should choose as the u and which we should choose for the dv, because we don't have any polynomials this time. So I'm just going to arbitrarily say this will be the u for the exponential, and the dv will be the trig. So we go ahead and, again, our standard little side thing. Don't forget to write this out. You do need to write this out. So the u is e to the x, so du is just e to the x dx, the derivative of the exponentials itself. Our dv was sine x, which means our v must be negative cosine x. Alright, and now we apply our integration by parts formula. So we now know that the integral of e to the x sine x, so that's our integral u dv, is equal to u times v. So u times v is e to the x cosine x, the negative in front. I just pulled it out in front there. So minus the integral, but again I'm pulling out the negative here, minus the integral of v du, so negative cosine x, made the plus be negative, and then the e to the x dx from the du. Alright, well how are we going to do this integral? So it looks like it didn't get any easier, but at least it didn't also get any harder, because before we had a exponential times a trig. Well, here we get an exponential times a trig. Well, let's just try integration by parts again and see where it gets us. So it's important that when you do these kind of deja vu type problems that you keep the same, so whatever pattern you used here, so here I let the u be the exponential and the dv was the trig, so it turns out you want to do that again, right? So here I want the u to be e to the x, and I want the dv to be the cosine x dx. So don't go ahead and switch it up, because if you accidentally say, oh, I did the exponential as the u this time, so for my second time I'll let it be the trig, then you're just undoing exactly what you just did, and we don't want to do that. So, alright, I got a little ahead of myself with my little sidetrack there, but again, I'm just rewriting negative e to the x cosine x, plus, and now I do the integration by parts on this. Now, one thing I should also point out is technically this is not the same u and v, right? I had a separate u and v here. I really should call them something different, you know, w and q or something like that, but it's so traditional to call it u and v. I'm just kind of overloading my variable names here, but hopefully there's no confusion. They're just symbolic notation to help us remember what the integration by parts formula is. So it's u times v, so e to the x sine x, minus the integral of v du, so the v is sine x, and the du is e to the x dx. So now you look at this and say, alright, I converted doing this integral the first time into this one, and then we did this integral, converted into doing this, but oh no, this is the same problem I started with, so I've just gotten myself into a horrible loop. Well, this is where the beauty of the deja vu technique comes in, because it turns out even though this is the same problem, that's okay, because we can take this and add it over to the other side. So when you do that, when I add this over to the other side, I get two of these, so it's 2 times the integral of e to the x sine x dx equals, and here I just pulled out the e to the x they had in common, so it's just sine x, and I wrote the minus one after it, so sine x minus cosine x. And now, to solve for the original problem, we just have to divide by 2. And then don't forget, add on your constant of integration. So we've solved it. The integral of e to the x sine x dx is equal to this crazy monstrosity, e to the x times sine x minus cosine x over 2 plus c. So those are the 3 most common kinds of sneaky applications of integration by parts, but usually things run more standard than that. But you will find out when you do some practice problems on your own. Alright, well, good luck with the integration by parts problems.